Welcome back. Let's look at some example problems of calculating work using vectors. Alright, so here's our first example. We want to find the work done by this force vector, which is equal to 4i minus 3j plus 2k along this distance vector, which is equal to negative I plus 2j plus 7k. Alright, so when you want to calculate work done by using vectors, there are two different formulas that you could use, and they look like this. For the first one, we have that work is equal to the dot product of the force vector and distance vector. And then for the second one, we have that work is equal to the magnitude of the force vector times the magnitude of the distance vector times cosine of theta, where theta is the angle between the force vector and the distance vector. All right, so these are your two options. One is to take the dot product of your vectors, and the other is to use the angle between those two vectors and their magnitudes. Technically, they are both the dot product. This is the standard form of the dot product, and this is called the alternate form of the dot product. But anyway, we use one of these formulas for when we don't know the angle between our force vector and distance vector, and we use the other formula for when we do know what that angle is. In this case, we don't know what that angle is, right? We're just given two vectors, the force vector and the distance vector, and we want to find the work done. So it makes the most sense for this example to calculate the work by taking the dot product of those two vectors the traditional way. So let's do that. Let's calculate the work in this problem. The work will be equal to the dot product of the force vector and the distance vector. And remember, to calculate the dot product of two vectors, you just take the sum of the product of corresponding components. So we multiply the x components together, add that to multiplying the y components together, and add that to multiplying the z components together. So let's do that. We'll have 4 times negative 1. Negative 1 is the coefficient of I, so that would be that x component. And so we'll have 4 times negative 1. All right, so 4 times negative 1. Then we'll add that to negative 3 times 2. So we'll have negative 3 times 2. And then we'll add that to 2 times 7. So we'll have 2 times 7. Okay, so we have the product of the x components, and then we're adding that to the product of the y components, and then we're adding that to the product of the z components. Okay, now if we simplify, 4 times negative 1 is negative 4, so this is equal to negative 4 plus negative 3 times 2, that's negative 6, so we have negative 6, plus 2 times 7, which is 14, so we have 14. Now negative 4 plus negative 6 is negative 10, plus 14 will give us positive 4. And so positive 4 is the work done by this force vector along this distance vector. Okay, now typically in a work problem there are units associated to that work, but in this case we weren't given any units. So an answer of just 4 is perfectly fine in this case. Okay, but in the future, make sure that you're on the lookout for any units in your problem because you want to make sure to tack those on to the end of your final answer. Okay? Let's take a look at another example. So next up we have a force represented by this force vector, which is equal to I plus 5j plus k, is applied to an object moving from point P, which is the point 3, 0, negative 7, to point Q, which is the point 2, negative 1, 0. Find the work done if the units of force are pounds and the units of distance are feet. All right, so this example is similar to our previous example, but it's slightly more involved. We now have units to work with, and our distance vector is not explicitly given to us. Instead, the distance that our object is traveling in this case is described by 2 points. It starts at point P and ends at point Q. And so if we want to find the distance vector for the object in this example, we need to find the vector that would connect those 2 points. Since the object moves from point P to point Q, vector PQ would be the distance vector. It would describe the path of motion for that object. Okay, so let's start by finding that our distance vector will be equal to vector PQ, and that vector will be equal to some x component times I plus some y component times j plus some z component times k. And we find those x, y, and z components by taking the coordinates of the terminal point and subtracting the coordinates of the initial point. Right? Our object starts at point P and ends at point Q, so P is the initial point and Q is the terminal point. So we'll have 2 minus 3 for our x component. So I'll write 2 minus 3. Then for the y component, we'll have -1 minus 0. So I'll write -1 minus 0. And then for the z component, we'll have 0 minus -7. So I'll write 0 minus -7. Now if we simplify, 2 minus 3 is -1. So this is equal to -1 times I. So I'll have -I plus -1 minus 0, which is just -1. So we'll have -1 times j. So we'll have plus -j, or we could just rewrite that to be minus j. So let's do that. We'll have minus j. And then we have plus 0 minus -7 times k. And 0 minus -7 is the same as 0 plus 7. So we'll have plus 7k. Okay? So that right there is our distance vector. It represents the distance that our object travels, or the path of motion. And so now that we have a force vector and a distance vector, we can calculate the work done in this problem. All right, and so remember, we have two different formulas to choose from. We can calculate work by taking the dot product of vector f and vector d, the force vector and a distance vector, or we can use this formula if we know the angle between those two vectors. In this case, we don't. We just have the two vectors, and so it's going to make sense once again to just take the dot product of those two vectors. So let's do that. Let's calculate the work in this problem. We'll have that the work is equal to the dot product of vector f and vector d, our force vector and distance vector, and that will be equal to the sum of the product of the x, y, and z components. So we'll start by multiplying the x components together. We have -1 times +1, right? -1 times +1. Then we'll add that to -1 times 5. So we'll have -1 times 5. And then we'll add that to 7 times 1, right? The coefficient of k is 1. So we have 7 times 1. Okay? Now if we simplify, -1 times 1 is -1. So this is equal to -1 plus -1 times 5. That's going to be -5. So we have -1 plus -5 plus 7 times 1, which is 7. So we have -1 plus -5. That's -6 plus 7 will give us an answer of 1. But in this case, that's not going to be our final answer. We also need to tack on some units because we are told to find the work done if the units of force are pounds and the units of distance are feet. In other words, our work units are going to be foot-pounds. All right, so in this case, our work was equal to 1, so our work is equal to 1 foot-pound. Since it's just 1, I'm not going to write the s there. The work is just a single foot-pound. Okay? And so that is the final answer to this example. Let's take a look at a different example. Okay, so next up we have a force of 20 newtons is applied to an object at an angle of 45 degrees to move it a distance of 10 meters. What is the work done by this force? All right, so this is a different example than what we've looked at so far. In this case, we aren't explicitly given any vectors, but we will be able to use vectors to represent this scenario. All right, because in this problem, we have some object, and that object is going to experience a force of 20 newtons applied to it at an angle of 45 degrees. All right, so if this is the horizontal for our object, then the force applied to it will look something like this, and we'll label it as vector F, or the force vector, and it creates an angle of 45 degrees with that horizontal. All right, that force is being applied to this object at a 45-degree angle. In particular, that force is a force of 20 newtons. And so I'll write down 20 newtons, but now what that actually represents is the magnitude of that force, right? 20 newtons is the amount of force applied to the object, so that means that the magnitude of the force vector is equal to 20 newtons. Okay, but then we're also told that because of that force, this object moves a distance of 10 meters. So our distance vector will look something like this. Our object is going to move straight forward a distance of 10 meters. And so the magnitude of our distance vector is 10 meters. All right, that is vector D, the distance vector. Okay, so in this problem, we're given three different things. we're given the magnitude of the force applied to an object, we're given the magnitude of the distance, or how far that object moves as a result of that force, and we're told the angle at which that force is applied, the angle between the force vector and the distance vector. And so I'll write that down yet as well. The angle between our two vectors is 45 degrees, which is the same as pi divided by 4 radians. Okay, the angle that the force vector makes with the path of motion is the same as the horizontal, which is 45 degrees. And so, in order to calculate work using vectors, remember that we have two different formulas. So far, we've only used this first one where we took the dot product of our two vectors. We're actually not going to be able to use that in this case, at least not in this form. We need to use this equation where we have the alternate form of the dot product, where we can use the magnitudes of the force and distance vectors as well as the angle between those two vectors. All right, so here's what we're going to have in this case. To find the work, we will take the magnitude of our force vector, which is 20 newtons, so we'll have 20 newtons, times the magnitude of the distance vector, which is 10 meters, so we'll have 10 meters, and then we're multiplying by cosine of theta, where theta is the angle between those two vectors. And so we will have cosine of that angle, which in this case is 45 degrees, or if you prefer to work in radians like I do, I'm going to use pi divided by 4. All right, so that's pi divided by 4. And if you don't remember how to convert from an angle in degrees to radians, I'll just show you real quick. An angle in degrees, if multiplied by pi divided by 180, will become an angle in radians. Okay, but maybe this is one that you have memorized. 45 degrees is one of those special angles that we typically memorize what it is in radians. All right, at least for me personally, I have this one memorized. 45 degrees is the same as pi divided by 4 radians. Okay, but if you don't have that memorized, don't worry. You don't even have to work in radians if you don't want to. Just make sure that when you plug cosine of 45 degrees into your calculator that you have it in degrees mode. Okay, but anyway, let's calculate the work here. 20 times 10 is 200. So we'll have that this is equal to 200 times cosine of pi divided by 4. And cosine of pi divided by 4 is the square root of 2 divided by 2. And so 200 divided by 2 is 100. So the work is equal to 100 square roots of 2. But then don't forget your units. In this case, we're working with newtons and meters. So our units are Newton meters. Or, if you remember from physics, or maybe in calculus 2 when we looked at work, Newton meters are the same as joules. That is a unit of work. All right, Newton meters and joules are the same thing. And so that would be the exact answer. But if you plug 100 times the square root of 2 into your calculator, you will find that that is approximately equal to 141.4 joules. Okay? And so that's how you can calculate the work done in this example. Let's take a look at another one. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so here's our next example. We have that a car is towed using a force of 1600 newtons. The chain used to pull the car makes a 25-degree angle with the horizontal. Find the work done in towing the car 2 kilometers. Alright, so this example is pretty similar to our previous example, except now we're working with a very specific object, a car. We're not just working with some unknown object in a random scenario. We have a pretty specific real-world scenario here where you might actually want to calculate work. And so let's draw a picture of what's going on here. We are working with a car that is being towed, so I'm going to do my best to draw a little car here. This isn't going to be a masterpiece, so don't laugh at me. Let me just draw a little car here quick. Not a great drawing, but that'll do. Those wheels are not connected to the car, but don't worry about that. Here, I'll draw a little window here yet. Usually my drawings are a little bit better than this. Anyway, that's going to be our car. And this car is being towed using a force of 1600 newtons. And that force is being applied through a chain that pulls the car at a 25-degree angle with the horizontal. All right, so this would be the horizontal. And then we're pulling the car with a chain that looks something like this. That's going to be our chain. And that angle between the chain and the horizontal is 25 degrees. Okay, and that chain also represents our force, right? The chain is used to pull the car, and so our force vector looks something like this. It's pointed in that direction. That's our force vector, and it is a force of 1600 newtons. That's actually the magnitude of our force vector. So I'll write that down, 1600 newtons. And then finally, we want to calculate the work done in towing this car 2 kilometers. All right, that's the magnitude of our distance vector. It's 2 kilometers, which would be the same as 2,000 meters, right? There's 1,000 meters in a kilometer, so 1,000 times 2 gives you 2,000 meters. Okay, typically we like to work with newtons and meters because then you can just write the units as joules when you calculate the work, but I'll give you both answers. I'll give you the Newton meters or joules as well as the Newton kilometers for our work, but we're not quite there yet. Let's quickly draw in our distance vector. That's going to be this vector right here, vector d. It represents a distance of 2,000 meters. And so we have everything written down here except for our angle here. This angle of 25 degrees represents the angle between our force vector and the horizontal, which would be the same as the path of motion represented by our distance vector. All right, the path of motion is going to be parallel to that distance vector. So 25 degrees also represents the angle between the force vector and that distance vector. Okay, so theta is equal to 25 degrees. And I'm going to keep it in degrees this time. I'm not going to work in radians because 25 degrees is not a special angle like 45 degrees or 30 or 60. So I'm just going to keep it like this and rely on my calculator. Okay, but remember, to calculate work using vectors, there's 2 formulas that we have to choose from. We can either calculate the dot product of the force and distance vectors in this way, or we can use the alternate form of the dot product where we need to use the angle between those 2 vectors, which is what we have to do in this case, right? We have the angle between our 2 vectors, and we have their magnitudes, which is the other part of this equation. And so this is the obvious choice in this case. We don't know the components of our force or distance vectors, so calculating their dot product the traditional way is not going to be the best course of action for this example. Okay, so let's set up our formula here. The work will be equal to the magnitude of the force vector, which is 1600 newtons. So we'll have 1600 newtons times the magnitude of the distance vector, which is 2 kilometers or 2,000 meters. So we'll have 2,000 meters. And then we're multiplying by cosine of the angle between those 2 vectors. So we have cosine of 25 degrees. Okay, now 1600 times 2,000 is 3,200,000. Not a very nice number to write down, but if you multiply that by cosine of 25 degrees in your calculator, you will find that the work done by the force is equal to 2,900,184.9 Newton meters, which would be the same as joules, right? I'll just write Newton meters in parentheses. And by the way, I did round off there. That's not an exact answer. I just rounded off to 0.9. But if you'd rather work in Newton kilometers, this answer would be a lot nicer. And so if you do that, this would also be equal to 2,900.18 Newton kilometers. Okay, and to get that answer, all I did was divide this one by 1,000. Because if this is in Newton meters, and you want Newton kilometers, there are 1,000 meters in a kilometer. So divide this by 1,000 and you get Newton kilometers. Okay, and so that is the work done in this problem. Let's take a look at one more example for this video. Okay, so here's our last example. We have to close a sliding barn door, a farmer pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees, as shown below. Find the work done in moving the door 12 feet to its closed position. All right, so as you can see, I already have a picture drawn here, unlike my car picture. I think this one's a little bit better because I took some extra time to draw it. But in this picture, we have our barn, and the sliding door for that barn is currently in its open position. Right, here's the opening to the barn that is currently open, so the sliding door is in the open position. In order for the barn to be closed, that door needs to slide over and block that opening. In order to do that, the sliding door needs to move a distance of 12 feet. All right, so 12 feet is that distance right here for the barn door to move from this position to this position. And so I have that path of motion represented by vector D. Hopefully you can see that. It was hard for me to choose a color in which you could see what I was writing here. Maybe I'll write over it in black. This is 12 feet right here, and that's our vector D. Okay, but then we have our little farmer dude down here who's pulling on this rope that's going to move that door into its closed position. He's pulling with a force, so that rope represents our force vector. And he's pulling such that there is a 60-degree angle with the path of motion. Okay, so the angle between vector D, the distance vector, and vector F, the force vector, is 60 degrees. And he's pulling on that rope with a force of 50 pounds. So we really have everything that we need to know in this problem in order to calculate the work. We have the angle between our two vectors, and we have the magnitude of those two vectors. The magnitude of the distance vector is 12 feet, and the magnitude of the force vector is 50 pounds. All right, so as you can imagine, if we're looking at our two equations for calculating work, we're not going to be using this equation. We don't have the components of our force and distance vector that we can use to perform the dot product the traditional way, so we're going to use our other formula by using the magnitude of our two vectors and the angle between them. Okay, so we know here that the magnitude of our force vector is equal to 50 pounds. The magnitude of our distance vector is equal to 12 feet, which even though I don't have it labeled in that color, that would be this distance, all right? And then the angle between those two vectors is 60 degrees. And that would be the same as pi divided by 3 radians. All right, that's one of those special angles that I have the radians memorized for. Okay, but anyway, let's set up our equation. The work will be equal to the magnitude of the force vector. So we'll have 50 pounds times the magnitude of the distance vector. So we'll have 12 feet. And then we're multiplying by cosine of the angle, which is 60 degrees, or pi divided by 3 radians. And so 50 times 12 is 600. So this is equal to 600 times cosine of pi divided by 3, which is 1/2. So we have 600 times 1/2, which is equal to 300. But of course, don't forget your units. We are working with feet and pounds, so our work units will be foot-pounds. Okay, and so 300 foot-pounds is the amount of work done in moving this sliding door of the barn to its closed position. And so with that, this was the last example for this video, but if you do want to see another example, I have another one available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.